So hi everybody. Thanks for coming. My name's David, as Nick mentioned. You can't tell by my facial hair. I've been here for way too long. I'm a 6-year PhD student at this point. And I oh yeah, does this thing work? No. Okay. Yeah, so as Nick mentioned, I'm co-advised by Mark Dredzy and Nicholas Andrews, and I currently live in New York. So if you don't recognize me, that's why. And today I want to talk a bit about a question that I've been scratching at for, I guess, about a year or so. And that question in its sort of shortest form is, where does negative transfer come from in multitask learning? Okay, that didn't work. Okay. All right, so I'll just start by talking about what multitask learning is and what I mean by negative transfer. So at face value, the term multitask learning is like extremely broad. I like to think of it generally as leveraging data from distinct distributions in order to benefit performance. But this is, again, very broad, very underspecified, right? We could think of lots of ways to sort of think about multitask learning. My first introduction to multitask learning was at EMNLP 2018, my first conference ever, where Lisa by Emma Struble et al. Won Best Paper Award. And Lisa trains different attention heads at different layers to predict different types of linguistic structures, so like dependency parsing, part of speech, etc. And the ultimate goal is to get the best semantic role labeler. And more recent familiar examples might be like instruction tuning, for example, where we fine tune a really large language model on hundreds of tasks simultaneously. And here the goal is to improve in context learning performance, right? And so the key idea here really is that we have labeled data for some sets of tasks, and we think that these tasks are related in some way. So here, for example, we have depth information and semantic labels for each pixel in a cityscapes dataset, in the cityscapes dataset. And if we're interested in both of these tasks, we might train a segmentation model on the segmentation labels and a depth model on the depth labels and call it a day. But of course, like, it's very intuitive to assume that these tasks have information that could be mutually beneficial, right? So predicting the depth of a pixel could help inform the model which pixels are near each other, which could be useful for semantic segmentation and vice versa. And so we want to share information between these tasks in some way, right? So how do we do that? Well, there's a lot of ways to do this in deep learning, and I'm not going to go over them. So instead, I'll just talk about the way that I do this and the way that I think most of multitask learning community does this, which is by sharing parameters across these tasks. This is sort of quote unquote like hard sharing method. And very generally, the way that this evolves is that you have some shared encoder, which has parameters that are used for all of your tasks. And this shared encoder takes inputs from some shared input space that's general across your tasks, and then maps them to some representation space, some hidden vector space. And then those representations are sent to task heads to map those representations to your task output space, right? And this is, again, probably the most popular form of multitask learning in deep learning. And to me, it's the most interesting because of how strict the inductive bias of multitask learning is on those shared parameters, right? And so what I mean by that is, in this model, the shared encoder, it has to generate representations that are generally useful for all of the tasks that you care about. So it needs to be able to take inputs and encode enough information in the representations that it generates that we can accurately use those representations to predict many tasks. And generally speaking, we keep the task-specific heads pretty small in capacity because we want the bulk of the learning to happen in the shared encoder, the shared parameters, right? So for example, for classification tasks, which in Cityscape is not a classification task, we would use like a linear layer with a softmax on top, so something very, very simple. And unfortunately, when we use this method for multitask learning, we often see curves that look like this, right? So here we have validation accuracy on the left and training loss on the right for 5 CFR 100 tasks as we increase the number of tasks that we train with from 1 to 20. And what we see is that, yeah, as we add more tasks, our generalization goes down, which sucks. And our training loss that we converge to goes up, right? And so it seems like as we add more tasks, we're starting to underfit those tasks more, and that's hurting generalization.
So on the left is task accuracy on tested.
Yes. Yeah. Okay, so let's talk about why that's happening, right? Why is it the case that our training loss is going up and our test accuracy is going down? So when we train our multitask models, we want to minimize the following objective, which is just the average loss of all of our tasks. And to do this, we usually use, for the shared parameters data, we use the average multitask gradient, which is just averaging the gradients of theta across all the tasks that we care about, right? And so we use that gradient for optimization. So even though we treat this as a single objective with a single gradient when we're doing gradient descent, in practice, we are still optimizing multiple objectives, and these objectives could conflict with each other, right? So specifically, we might have conflict in the gradients of theta across different tasks. And this conflict can arise in a couple different ways. Here I have a couple examples of sort of what that conflict might look like. But generally speaking, we can just think of this as when our gradients for task A are sort of pulling in a different direction than the gradients for task B, we're struggling to sort of minimize the loss for tasks A and B jointly, right? This is called gradient conflict or task conflict, and it's thought to be a really big problem in multitask learning. And so, yeah, so if we turn to our example, we can definitely see evidence of multitask conflict, right? The losses that we converge to for the higher numbers of task models are higher, right? So we're struggling to fit the losses as well as we want to. So conflict is definitely happening, and that is correlated with our generalization accuracy going down. So it seems like conflict is causing us to underfit our tasks, and that underfitting is causing negative transfer, right? And this is bad. Additionally, there's also been work that suggests that conflict and negative transfer are highly correlated in other ways. So for example, last year at EMNLP, we had a findings paper where we studied gradient conflict and negative transfer in two different multitask NLP architectures. And what we found is that gradient conflict and negative transfer were largely consistent. So not only does this suggest that conflict and negative transfer are really correlated, but also that they're kind of intrinsic to the tasks and less so to the architectures that we're using to train these tasks. So given that we believe that task conflict is leading to underfitting, which is leading to negative transfer, there's been a lot of recent work that has tried to address task conflict by altering the gradients that we use during optimization, right? So a few examples of these would be like MGDA, PC grad, grad norm, grad drop, CA grad. Can you see a theme here? Most of these methods are focused on either balancing the rate at which tasks are learned or directly altering the gradients to step in directions that are less conflicting across different tasks, right? And so most of these methods, of course, report really strong results on the baselines that they consider. But if you have worked with these methods like I have, you probably know that these methods don't actually work as advertised most of the time. It's actually really hard to get them to improve generalization. And last year at Europe's, there were two papers that kind of came out simultaneously, which is pretty funny. And both of them were sort of exploring whether or not these multitask optimization methods actually help. And so in particular, Jin et al. Found that these methods don't actually converge to a different Pareto curve on the loss surface. So they're not actually even improving underfitting compared to just sort of the average gradient that the sort of naive baseline that we all use, right? And perhaps more interestingly, Curran et al. At the same conference found that these methods may actually act as regularizers, right? So they show that if you use L2 regularization with a uniform average multitask gradient, you get very comparable performance to these multitask methods. Yeah.
Can you give us a little intuition about what these methods are trying to do? For example, are they like scaling down directions in which the tasks tend to conflict?
Yes, they basically like I guess so. Going back to this diagram, it's hard to sort of envision in one dimension, but there's sort of two different types of conflict that are typically addressed. So there's directional conflict. So if gradients are pointing in different directions, we'll try to find a gradient that may not be the average, but instead is some nice combination such that if we move in that direction, we're still minimizing the loss for all of the tasks in some equal way, right? So we're not biased towards tasks. And then magnitude conflict is the same thing, but we're sort of more concerned about the magnitude of one task versus the other, and we want to balance those two things.
So every mini batch, maybe, it should help all the tasks.
Exactly, yeah.
Maybe not every example.
Right, yeah. Okay, so I want to talk a little bit about the last thing I just mentioned, which is that multitask optimizers act as regularizers. And that's pretty curious because it's pretty counterintuitive, right? The idea that multitask models need regularization. Because again, we saw that our models are underfitting, right? So we're underfitting the loss because of task conflict. So why would we add L2 regularization on top of that if we're already underfitting? And is it the case that multitask models are sort of overfitting in some implicit way, right? And so to study this, we evaluate the entire training loss of our data set at each epoch. And our generalization, our test accuracy, we plot that here. And what we find is that, yes, so task conflict absolutely happens. So we're not able to achieve the same loss values that the single task model does with the multitask model. But even for loss values that we're still able to achieve with the multitask model, we're already experiencing negative transfer, right? So we are overfitting in some implicit sense. It's not just a matter of our 0th order loss isn't going down as much as we want it to. There's something implicit at play here, right? As an example, if we had set our convergence stopping point at 10⁻⁻3, we wouldn't even observe conflict as something that's prohibitive, right? But we would still have negative transfer. And this happens in a bunch of multitask settings. So here we're looking at cityscapes, and we can see semantic segmentation on the left, very similar story. And for depth estimation, we're actually seeing positive transfer because here lower is better. But again, the same story, right? We're not getting positive transfer because we're fitting the tasks better. We're getting positive transfer because of some implicit factors. If we look at individual tasks for CFAR 100 again, the same story, right? Here for the task food container, we're even fitting the loss down to down to 4 decimal places, within 4 decimal places of the single task loss, still experiencing lots of negative transfer. And finally, we see the same thing happening in our MNIST data sets, where we train a single model on multiple MNIST-like data sets. So a very similar story. This is happening in all of our multitask settings, right? So this is sort of the first key conclusion that I want to highlight, right? So when we run multitask models, and we're so often that are so often used as baselines for our multitask optimization method papers, what we see is that by and large, negative transfer is happening because of some kind of implicit overfitting rather than underfitting due to task conflict, right? So in other words, negative transfer isn't really explained by how well we fit the 0th order loss, and that may or may not be surprising to you, right? So we're interested in explaining this generalization gap, right? So yes, we do have task conflict, but why are we experiencing negative transfer even for loss values that are comparable? And so to answer this question, I'm going to turn to a phenomenon in which we see a very similar type of generalization gap appear in deep learning, right? And that is the large batch generalization gap. So this is a phenomenon in deep learning that, or it used to be fairly common knowledge that using a small batch size for your deep neural network would give you better generalization than a large batch size, right? And there's a lot of speculation as to why this is, and a lot of people would believe that it's because you need some amount of noise early into training to sort of escape bad minima and land in large, sort of wider basins of attraction that generalize better, right? That's the sort of hypothesis. And it's also worth noting that this is not unique to neural networks. So for example, Liang and Klein in 2009 found a similar result for mini batch expectation maximization. So smaller batches led to better generalization in some of their settings. But an oddity in deep neural networks is that if you scale the learning rate by the same factor as you scale the batch size, you can actually maintain the same generalization for a larger batch size, right? So this is called the linear scaling rule. And it's weird because the noisiness of optimization as it's determined by your gradient covariance should scale quadratically with your learning rate and linearly with your batch size, or like inversely, right? And so what that would suggest is that if we wanted to keep the noise of our optimization problem the same, we should scale the learning rate by the square root of the factor that we scaled the batch size. But instead, the ratio that seems to be sort of determining generalization is this linear ratio of the learning rate over the batch size. And this ratio is sometimes called the temperature of optimization, which is, of course, a very overloaded term. And yeah, so this ratio was sort of found by Boyal and Keskar around 2016, 2017, kind of at the same time. And so, yeah, so it's important to note that like in single task settings, if we sort of vary the batch size but keep everything constant, we see a very, very similar story as to what we were seeing with negative transfer between multitask and single task models, right? So we have a generalization gap, even though we're achieving similar loss values. And so we want to know whether or not negative transfer that we see, the generalization gap that we see in negative transfer between multitask models and single task models, is that due to similar mechanisms as the large batch generalization gap, right? And so one thing to note is what is the noise of our multitask gradient? And it's really determined on how we aggregate the gradients. And this is sort of an important point because it's not something that a lot of people have highlighted. But so if we recall that I was sort of presenting the gradient that we use as the average task gradient, if I replace that averaging term with C instead, just some generic value instead of the number of tasks, then the gradient covariance, if we sample our task examples independently, is the sum of the covariance of all of our tasks divided by c squared, right? And so what's important here to note is that if we're using the average gradient, what we're doing to our gradient covariance is we're dividing it by the number of tasks squared, right? This is a really significant effect that we're having on the noise of our gradient covariance. And does this impact generalization? Yes, it has a significant impact on generalization, right? So here we're looking at CFR 100 and CLSP. We're keeping everything constant here. These are multitask models. We're keeping everything constant here except for what term we use to aggregate the task gradients during optimization. And what we find is that the term that we use to aggregate has very little effect on the loss that we converge to eventually, but it has a huge effect on what generalization we see towards the end of training. In particular, if we use c equals 1, so if we're summing, we have mitigated a significant amount of negative transfer that is reported in a lot of these multitask optimization papers, right? Just by changing essentially the learning rate that we're using at each step for our shared parameters. And yeah, so perhaps most critically, we also find that the efficacy of conflict mitigation methods goes down if we are sort of aware of how we need to scale factors like C, the learning rate, and our batch size during optimization. So here we have, on the left, we have a sort of low temperature setting, and we see that single task models are significantly beating multitask models. We have a lot of negative transfer. And then these multitask optimization methods are helping a lot, right? So here, for example, PC grad, which is orange, is doing a lot to recover negative transfer. But if we move over to the right, to the high temperature setting, not only is our sort of uniform average baseline doing a lot to mitigate negative transfer, it is also now beating all of these multitask optimization methods that are supposed to be addressing negative transfer, right? And again, I just want to emphasize that we've done all of this without really addressing task conflict in the sense that we think we need to alter gradients or sort of balance task weights. All we've done is change the noise level of our optimization process, and we've seen a lot of impact on negative transfer, right? Okay, so finally, I want to spend a bit of time digging a bit deeper into this idea of implicit overfitting and how it relates to multitask learning. And this work is going to be work that we're sort of working on recently. This is very new stuff. It's not in any papers that I've talked about. So we've seen that just tuning our hyperparameters with the linear scaling rule in mind can go a long way towards addressing negative transfer, but it's certainly not the case that we've completely eliminated negative transfer, right? Negative transfer still exists in some of the tasks. And what we want to know is whether or not the remaining negative transfer that we see can be explained by the same factors that are sort of eliminating the gap between averaging and summing gradients, right? So are we just sort of not tuning our temperature enough? Could we do even more with respect to our hyperparameters, and then that would eliminate the negative transfer that we see? Or is it something else, right? And yeah, we want to sort of explain, or we would like to be able to explain also why we see positive transfer in some settings, right? So here, when we average, we have negative transfer. When we sum the gradients, we have positive transfer. And we would love to know if the reason that we're getting positive transfer here is because of, over the single task models, is because of the same factors that are sort of giving us better generalization over the average multitask gradient, right? So to really dig into this, we need to actually understand why the linear scaling rule works, right? Why does it hold? It's sort of a curiosity, and it's not something that's perfectly understood. So I previously mentioned that a prior hypothesis is that more noise of the correct type, and I say correct type because you can't just add like Gaussian noise to your gradient. It really is dependent on your batch size. But that more noise of the correct type can lead us to flatter regions, flatter minima in the loss landscape, right? But it's recently become a more and more sort of popular notion that flatness is not actually connected to generalization as tightly as we think. In particular, a work that I'm not citing here, but the edge of stability work by Cohen et al. Showed that the sort of max eigenvalue of your Hessian that you converge to is really determined by your learning rate, rather than any other properties of your optimization. And here, sort of follow-up work by Carr et al. Showed that so flatness of your solution that you converge to as determined by the max eigenvalue of your Hessian is determined by your learning rate, but your generalization is still determined by the linear scaling rule, right? So if you scale the batch size with your learning rate, you maintain generalization, but the flatness of the solution you converge to is changed quite a bit, right? So flatness does not quite explain what we're looking at here, right? This linear scaling rule property. So to attempt to sort of understand this better, Smith et al. Try to answer what the gradient flow of what the loss function that a gradient flow would be minimizing is if we are using small batch sizes and large learning rates, right? And so here we can think of gradient flow as sort of a continuous time version of gradient descent. So if we were taking full batch gradient descent with infinitesimally small step sizes, we'd essentially be approximating gradient flow with gradient descent. And you can think of it as we'd just be following sort of like the curve of the direction of steepest descent in a continuous fashion, right? But of course, we don't actually take infinitesimally small step sizes, nor do we use full batch gradient descent most of the time. We're taking large step sizes with small batch sizes. I keep getting those two confused. And so what Smith et al. Tried to do in their 2021 paper is to derive what that modified loss is that yields a gradient flow that matches our model trajectories in practice when we're using small batch sizes, large learning rates. Wow, that's really giving me a tough time. And so what they find is this value, and this is kind of ugly, but just bear with me, right? So essentially, they show that the gradient flow of our models can be modeled by this loss function. And this modified loss has both the loss that we care about, so that's L theta, and then this additional bias term, which minimizes the gradient norm of our batches, right? And so this term depends on the batch size that we use during optimization. And this bias term can also be broken up into two distinct terms, right? So the first of those is a bias towards low gradient norms of L theta. So that's the entire data set, the entire gradient of our data set averaged together, right? And what's the difference between the bias of the full batch gradient norm versus low norms for individual batches? That is, intuitively, if you think about it, we could have a small total gradient norm in a couple of ways, right? So we could have individual samples that all have small gradients, and so when you average them together, the gradient norm is small. Or we could have individual samples whose gradient norms are large, but they all point in different directions. And so again, we have a small total gradient norm, right? And so this bias towards small batch gradient norms includes this bias towards a low total gradient norm and a bias towards a low covariance trace, right? So we want our gradients to point in the same directions, or we want these gradients to be coherent, right? And this bias term in particular, they posit, is what explains the linear scaling rule. So here we can see the linear scaling rule as a coefficient of this term, right? So eta over b, that's learning rate over batch size, times the trace of your gradient covariance. And the idea is that this term, this bias in this modified loss, is what is being optimized by the linear scaling rule, right? So this is what sort of keeps our generalization constant. And yeah, so this has been sort of, this was corroborated very recently by a paper by Novak et al. It says 2022, but it was actually published, I think, iClear 2023. And to my understanding, this is sort of the best understanding that we have of why the linear scaling rule holds in practice, right? So now we're going to go back to negative transfer. Sorry, it's a long tangent. So we want to know if generalization gaps that we still observe are due to this implicit factor, this small batch gradient norm, or this bias. Oh yeah, sorry.
Just a question on the previous slide.
Yeah.
Just like sort of all these like regularizers that try to keep the batch like sort of coherent and the individual gradients coherent. Does this work nicely with like modern schedulers as well?
There's a great question, and I think the answer is.
Could you repeat the question?
Like this sort of regularization scheme where the total batch has to behave nicely with respect to the individual gradients, and the individual gradients also have to behave nicely. I asked if it works cohesively with modern schedulers, modern learning rate schedulers.
Yeah. So the answer is no, I'm pretty sure.
Okay.
I think our understanding of how this evolves under, say, even just like Atom.
Like schedules, you just mean that the general learning rate decays over time.
Yeah.
Oh,
Yeah.
Yeah. So how this regularization term plays under Atom, for example, is I think very unclear. And I want to say that there was a paper that has been trying to disentangle these, but it's like really not clear how these terms are relevant when you're using something like Atom. In these cases, so we are using momentum, and momentum does seem to follow the same sort of rules that vanilla SGD does. So obviously these results are derived from SGD, but when we use momentum, we see that they sort of the same sort of terms kind of rise up. And in particular, that was also found in this Novak et al. Paper. They use momentum. And in the settings that we're considering, momentum gives us the best generalization out of all the optimizers that we could use. So that's nice for us. But yeah, definitely Atom, I think, would change the story quite a bit.
Okay.
Yeah. Okay, yeah, so now we go back to negative transfer, and we want to know if the generalization gaps that we observe, the sort of remaining generalization gaps that we observe are still due to these factors, these sort of implicit regularization terms. In other words, are we not optimizing these regularization terms enough, and that's why we're getting negative transfer? Are we optimizing them more than single task models are? Is that why we're getting positive transfer? And of course, the answer is no, right? So like nothing's ever that easy. So here we return to single task models compared to average gradients and the sum of gradients. And we see that we do have a significant difference in gradient coherence between between averaging and summing. So the sort of linear scaling rule that we're taking care of when we sum the gradients rather than averaging them is having a huge effect on our gradient coherence. But the difference between summing multitask models and the single task gradient coherence is not really significant. And our generalization gap still is pretty large, right? So it doesn't seem like this idea of gradient coherence is really explaining the remaining negative transfer that we have. So we've done our due diligence in making sure that the temperature of optimization is correct. But the remaining negative transfer is not explained by any more factors that are related to this temperature of optimization. And yeah, it's this sort of same story for positive transfer, right? So here we see a significant amount of positive transfer for when we sum the multitask gradients. And again, we see a gap in gradient coherence between averaging and summing, and we see a gap in generalization between averaging and summing, but we see a gap between summing and the single task models, and that gap is not explained by gradient coherence anymore, right? So now we have positive transfer, but that positive transfer isn't being explained by these implicit factors that we're optimizing when we, sum versus average our gradients. Okay, and so that's where I'll wrap up. So I guess like in conclusion, a pet peeve of mine, I guess, when you develop a new method, you should verify that it's actually solving the problem that you developed it for, right? So a lot of these multitask conflict optimizers are guilty of this, I think. They take a better number and they assume that they've actually addressed conflict when really they may have actually just been acting as early stoppers or regularizers. Yeah, when it comes to negative transfer, we can show that a lot of the reported negative transfer in these task conflict optimization papers is really due to sort of implicit factors around like the temperature of optimization, and that we can do a lot to mitigate negative transfer if we're just aware of these implicit factors. But finally, we can't explain all of transfer that we observe with these implicit factors. And so there's sort of still this big question mark as to like, how do we sort of capture when we're getting positive transfer with some factors that are tied to optimization, because we can't seem to get it from conflict. We can't get it from implicit regularization. It doesn't come from the flatness of our minima. So we're still sort of missing some mechanism to describe transfer in multitask learning. And I'm really interested in what that mechanism is, but I need to graduate. So one of you can figure it out maybe. Yeah, so I'll take questions now. Thank you for listening.